So solving field equations. The electromagnetic potential A mu on X can be expanded in the Fourier integral. So let's write down this expansion. A mu on X is C over 2/3 integral dk divided by square root of 2c modulus of k. This is put for the moment for convenience, but you will see that and this is the same thing as you usually do when you expand electromagnetic field in the Fourier series. And then here I will write the amplitude A mu depending on time and k and possibly on lambda exponential I kx. So that's an expansion of electromagnetic field in the three-dimensional Fourier integral. And as usual with differential equations, this is a way to solve this linear differential equation is to use Fourier space, because then this differential equation in the Fourier space becomes a system of algebraic equations, turns into a system of algebraic equations. Now, we are not expanding over time, so time is not involved, and that's why this amplitude does depend on time. If you just, yeah, maybe I will say something about k. So k multiplied with x, this is scalar product ki xi, and this is the same as minus ki xi because of the Minkowski metric. So if you take this Fourier expansion and plug it into the equation box A mu plus lambda minus 1 d mu d nu a nu equals to 0, then your equation gives the following system of coupled equations. So first, you take index mu to be 0. You can put this index down, and then you get the following: lambda A0 double dot. So A here, this is this amplitude which I have introduced. This curly A. So curly A, how I write it? Curly A 0 plus C squared A squared curly A 0 minus I lambda minus 1 C ki curly A dot is equal to 0. That's the first equation. And the second equations are equations for a curly AI, and they look like AI double dot plus C squared K squared A curly I plus I lambda minus 1 C Ki A curly 0 dot plus lambda minus 1 C squared Ki Kj A curly J equals to 0. So you get such a system of now ordinary differential equation with respect to time. On this component of amplitudes here, Ki, Ai. Okay, this is how equations now look like, and we have to solve them. To solve this system, what we do, we can take the second equation and multiply it with Ki. this equation, multiply it with ki, and introduce extra variable chi, which is ki a curly I. Like this. Then the system can be rewritten in the following way. So lambda a curly double dot 0 minus I lambda minus 1 c chi dot plus c squared k0 squared a0. I will tell you what is k0 in a second. And the second equation will be chi double dot plus I lambda minus 1 c k0 squared a0 dot plus lambda c squared k0 squared chi is equal to 0. Now you see you have two equations which involve two variables, a0 and chi, and there is nothing else. And here k0 squared by definition is ki the same as k vector squared by definition. So you get such a system of two ordinary differential equations for the variables a0 and chi. And this can be solved by setting up the following ansatz. A0, you take exponential minus I omega t. That is something which you actually expect from free oscillators. Time dependence for free oscillators set for normal, say, vector field, you expect the appearance of such a exponential. But then in order to actually remove these linear terms, you need to assume that there is an extra linear dependence on time, where here I put h0 and a as constant coefficients, which I have to determine. And the similar ansatz for chi, minus I omega t. Let's put here u plus bt. So variables which I have here in this ansatz for the solution, and which I have to determine is h0, a, u, and b, which are constants. So you see, it's kind of a little bit unusual ansatz for the solution because it involves the linear t dependence. But this is needed if you want to kind of remove these extra terms which are linear in derivatives, in time derivatives. So this means that now what I have to do is to substitute these expressions into these equations. So this which I have to substitute. And after I do this, I'm left with the following equations. So let me write them down. C squared k0 squared minus omega squared lambda multiply by h0 minus ICB lambda minus 1 minus c u omega lambda minus 1 plus 2ia omega lambda. This is a one part plus t-dependent part. C squared k squared 0a minus cb omega lambda minus 1 minus a omega squared lambda is equal to 0. That's the first equation. And the second equation is lambda c squared k0 squared minus omega squared u minus 2ib omega plus ic h0, no, k0 squared multiply with a lambda minus 1 plus ch0 k0 squared omega lambda minus 1 plus t-dependent part lambda c squared k0 squared b minus b omega squared plus c k0 squared a omega lambda minus 1, and this is all equal to 0. So you get these two equations. I mean, you don't need to remember these formulas. It's just straightforward substitution of the ansatz A0 and chi into these equations will produce for you these expressions. And in fact, what you would like is that these equations are satisfied for any value of t. And for any value of t, to satisfy these equations, you understand that then, for instance, in the first equation, this expression in the bracket must be equal to 0. And then if it's equal to 0, then this part here also should be equal to 0 separately. If we insist on satisfaction of these equations for any value of time. And from this requirement, we can actually find A and B, because you see, then these are coupled equations for A and B. And from these equations, we can find A and B, and actually substituting then in the second equation, A and B, we will find only one condition. We will find that second equation is satisfied for any t, provided omega, this variable omega, is related to k0 in the following way. Either omega squared must be equal to c squared k0 squared, from where you conclude that omega may take values c modulus of k0, or omega is equal to minus c modulus of k0. So you have two possibilities for omega. And from the first equation, you find the following solution. So if you pick up, for instance, omega to be equal to of k0, then for A and B, you find the following solutions. So variable A is IC lambda minus 1 divided by lambda plus 1, H0 K0 plus U, and B is minus IC K0 lambda minus 1 divided by lambda plus 1, H0 K0 plus U. So let me remind that H0 and U, these are two variables which are constants entering the ansatz for A0 and chi, and A and B we have determined through this H0 and U. And this is how they look like. So in particular, you also see that there is one special point, lambda is equal to minus 1, which we have not discussed before. Also, you see that what is nice is that the case lambda equals to 1 actually makes this choice, makes A and B to be equal to 0, and if this 0, then these terms linear in T do not arise. But in general case, for general lambda, A and B are non-trivial, and the point lambda is equal to minus 1 is a dangerous point, which I also would like to exclude. Somehow it will bring me singularities. A and B becomes infinite at that point. That is something which I don't want. So lambda minus 1 should be also discarded for the reason of having regular expressions, and lambda is equal to 0 should be also discarded because it's a Maxwell case. So lambda is equal to 0 and minus 1. These are 2 points which I have to avoid. Otherwise, lambda remains to be arbitrary. Now, at this point, H0 and U remain to be undetermined. From these two equations, I cannot get any more information about these variables H0 and U. So these two variables, they remain for the moment undetermined. But on the other hand, I did not yet explode this full system of equations. I've just projected the second equation by ki, but I did not actually explode the three equations which I have for indices I running 1, 2, 3. I have considered so far projection by means of pairing this with ki. This means that in order to explode these equations in full, what I have to do is I have to introduce the ansatz for AI purely, and I'll do it in the same way. So minus I omega t, hi plus ri multiply with t. So introduce 3 new h's and 3 new ri's, and I'm keeping omega to be ck0. ck0. So k0 I consider to be positive. Then if I plug this ansatz for AI into the expression, into the differential equation for AI here, and again separate the time-dependent part from a time-independent part, I can actually solve for this Ri in a unique way, and I find that this is ICKI divided by K0 multiplied by lambda minus 1, lambda plus 1, H0 K0 plus U, and this turns out to be the same as KI K0 squared multiplied with coefficient B, which we have already determined. If you compare this with an expression for B, here is B, you see that this is exactly Ki divided by K0 squared multiplied by coefficient B. And finally, this solution for AI, where HI constants remain to be undetermined and Ri are determined, must satisfy the compatibility condition, because as you remember, we have introduced chi to be Ki AI. And so this chi then is exponential minus I omega t, and I take my ansatz and multiply it with ki, so I get hi ki plus ki rit, like this. And this must be equal to our ansatz, must coincide with the ansatz we have taken for chi, which is minus I omega t. Remember, u plus bt. U plus bt. So from here, you immediately compare the terms linear in T, and you derive that B is actually Ki Ri. Which is also obvious from this expression, right? Because if you pair it with Ki, you get Ki squared, but Ki squared is the same as K0 squared. And so they canceled, and you get that B is Ki Ri. And also U is, comparing this term with this one, you see that variable U, which was originally undetermined, becomes Hi Ki. So nicely, when we come back to the variables A and B, so what's an A and B? You see, A is IC lambda minus 1 divided by lambda plus 1, H0 K0. I'm looking at this expression here. Let's take and make it in green. I come back to this expression, and now I know what U is. U is Hi Ki, and I conclude that this expression becomes covariant pairing between H mu and K mu. This is how it looks like. And an expression for B, which is this one. Let's make it yellow. Also, if I substitute here U, then it becomes equal to B, which is minus I C K0 K0 multiplied by lambda minus 1 divided by lambda plus 1 H mu K mu. So this is our expressions for H and B, for A and B, and therefore if you now look at the whole system of equations, you realize that we have used all the information from these equations we can have, and all variables are in fact determined except H mu. So H mu remain undetermined at this point, and the expressions for the component A0, A curly 0, 0 on T and K, takes the following form. If you come back to our answers, it's minus I omega T, H0 plus I H mu K mu, multiplied by lambda minus 1 divided by lambda plus 1, Ct, and A curly I on Tk is equal exponential minus I omega T, Hi plus I H mu K mu, Ki divided by K0 squared, lambda minus 1 divided by lambda plus 1, Ct. And so this is what is here is a solution of my equations of motion in the Fourier space. So this is how solution looks like. And it's characterized by these variables H mu, which must contain in it the creation and annihilation operators for electromagnetic field. Do you have any questions here on the procedure? This is how these solutions look like. They are not exactly the plane waves, because now they involve these extra terms which are linearly depend on time. But this is only a solution. You can just forget about everything, take these potentials A0 and I, substitute them in the equation of motion, and the original equations of motion I've written down here, and here, and here, and these equations here, and you will see that they will be satisfied. They will be satisfied. No questions? Okay. Then actually you see the structure of the equations, the structure of the electromagnetic potential in this new setting is the following. So electromagnetic potential depending on T and K, and for convenience we write it in a concise form like this. We write it like this. So minus I omega T, here some U depending on mu on Tk. And this variable U depending on mu on Tk, I just put it concisely as H mu plus I H mu K mu, K mu divided by K0. Sorry, there is no here square. At this point, there is no square, just K0. This K0 is positive, so Ki divided by K0. So K mu divided by K0, lambda minus 1, lambda plus 1, Ct. Yeah, question? You see, these two formulas combined covariantly because here is H0 corresponding to A0, here is AI corresponding to HI, and then I can combine these two formulas in one, where A mu with a 4 index mu is equal to exponential minus I omega t u mu, where u mu is this expression here. Here I have to put actually probably another index to prevent the confusion. Let me put here index nu. Over index nu, there is a pairing, and index mu is the same as index mu standing on the left-hand side here.
Professor.
Yeah.
In this amplitude that you found, I can see for this linear term in time. For example, in the future behavior of this, we will have some oscillation, but the amplitude of this will be divergent. So I don't understand in the behavior of this in the far future. This field.
No, this is yeah. So this is the terms which involve in this T. As you see, they're proportional to lambda. They have a lambda dependence in them. That means that in actually, that's coming back to our discussion of the role of this parameter lambda. Though these terms are present in the explicit solution here, at the end of the day, making computation for the gauge invariant observables, these terms somehow should not contribute. They should decouple.
Okay.
They should decouple. But otherwise, I have not done anything. I just honestly solve these equations of motion. And what I found is that there is a freedom in this solution, and the freedom is described by the 4-vector H mu. H mu is a 4-vector which is arbitrary for the moment, and equations of motion are satisfied just with an arbitrary H mu, identically satisfied. Now, the full solution, coming back to this solution in X space, as we know that what we computed are Fourier components, and therefore the solution in X space will look like this. So A mu on X is C 2 pi 3 over 2 integral dk over square root of 2 omega to omega, and then this u mu on tk u mu on tk like this, exponential minus I k multiplied by x. So now I take into account the dependence on time. So it's kx is a product of 4 vectors, scalar product of 4 vectors. And then the contribution of terms where omega is equal to minus ck0 with k0 positive. This is the second branch of the solutions. This will just lead to appearance of the complex conjugate of this amplitude u mu. So with u mu complex conjugate depending on tk, and then there will be ikx. That's the second branch. So this is how electromagnetic potential looks like. So essentially, this solution looks like the normal decomposition of the 4 vector you would expect. The only thing is that these amplitudes, u mu, have now extra dependence on time. So in general, you see that this solution is not exactly the plane wave decomposition, but it's a more complicated thing because this amplitudes have non-trivial dependence on time, linear dependence on time. Okay, now you can compute out of this the momentum, because you know what is momentum. Momentum is something which we have introduced at the beginning of our discussion. So where was the canonical momentum? So here is the P mu. So you take this expansion for a mu and plug into this formula, and that allows you to compute this momentum P mu, right? P mu out of the field expansion given by this formula here. And so then what you will do, you will take expression for P mu and A nu, and you know that P mu on X and A nu on Y satisfy the standard canonical bracket. So this is what comes out from the standard canonical quantization procedure a la Dirac. We replace the Poisson bracket with the quantum Poisson bracket, which is commutator. So this is what you would get. P on X and with A nu on Y, commutator is given by delta function essentially, and all the other commutators between P and A are equal to 0. So canonical structure. And now what you do, you take an expression for A nu given by this formula here. Take P mu as given by expression for canonical momentum, where you substitute this expression for A mu. And then you will see that this commutation relation between P and A will result into non-trivial commutation relation between H's. So H's, this H's A mu, which we have not defined, these are which are undetermined, so not defined, but undetermined. These are variables which somehow must contain inside the creation annihilation operators for our electromagnetic field. And so you can do this computation. It's a little bit tedious, but otherwise there is nothing special. And you will find the following commutation relations between these modes, between these H's. And it turns out that it's a nice actually expression where you have delta K minus K prime, K minus K prime, multiply with the matrix M mu nu, M mu nu, where this matrix M mu nu has the following structure. This matrix M, it's a matrix which is 4 by 4, right? Because in this is mu and nu running from running 0, 1, 2, 3. And so we have a symmetric 4 by 4 matrix where the element, the first element is a lambda plus 1 divided by 2 lambda. Then there are here on the diagonal, there will be minus delta ij plus ki kj divided by 2 k0 squared lambda minus 1 divided by lambda. And this first row will contain then only zeros here, and the first column will also contain here all zeros. So it's like first row, first column, and then here in this block are 3 by 3 matrix. Here in this block there is a 3 by 3 matrix, which components are explicitly given by this expression here, minus delta ij plus ki kj divided by the 2 k0 squared lambda minus 1 divided by lambda.
Professor, here h mu and h nu dagger correspond to creation and annihilation operator.
Yeah, so this is the same, yes. So when you quantize, then this is complex conjugate becomes dagger, and h in it, h which sits in A becomes h dagger mu, because it is inside. You see it here is h. It is inside u mu, and here this will be h mu inside, but it sits. But now it becomes an operator. Upon quantization, it becomes an operator, and the canonical commutation relations between p mu and a nu induce the commutation relation between the components of H. And this is how it looks like. This is what you find. Actually, you see that for the case of lambda equals to 1, it's interesting, right? That lambda is equal to 1. Here, the first component simply becomes 1. So matrix becomes 1. 0, 0, and here for lambda is equal to 1, this term depending on case disappear, and you get okay. So if you write it in terms of components, this 4x4 matrix, then you will find 1, minus 1, minus 1, minus 1. This is because of minus delta ij, and zeros on all other places. And this is nothing else as Minkowski metric, as you realized. So in the case of lambda is equal to 1, here on the right-hand side, you just get Minkowski metric for lambda is equal to 1.
Professor, can we somehow relate lambda to the charge of the electromagnetic field?
No, no. Lambda is just, again, lambda is a constant parameter. It's not a charge. It's not a charge. It's some constant. You can fix it 1, 10, 5. The only thing you don't want to fix it is lambda is equal to 0. That's because of singularity. Yes. And this is singularity of Maxwell. Because at lambda 0, you have Maxwell theory, you see that you are in trouble then. Because then this matrix becomes singular. Yeah. So lambda is equal to 0, you have to prevent. And lambda is equal to minus 1, as we said in some computations. Then these amplitudes become ill-defined because of lambda is equal to minus 1. So these 2 points you avoid. Otherwise, lambda is some constant, which you may fix at your will. It's not a charge. It has nothing to do with the charge. Charge arises only when you couple. I mean, we consider the free theory of electromagnetic field. There are no charges here at all. Charges describe charges we associate with metafields. Because and this is just free electromagnetic waves.
Yes, we charge electromagnetic field.
Well, electromagnetic field by itself, you cannot say that it's charged.
Yes,
photons are not charged with respect to photons. Charge arises when you take a material particle like an electron or positron, and the fact that this meta field like electron or positron interacts with photons, interacts with the electromagnetic field, we say that this phenomenon of interaction we associate with the fact that electron and positron carry charge with respect to electromagnetic field. So they interact with electromagnetic field. And charge is simply describes the strength of interaction between electric and magnetic field. So between electromagnetic field and the meta field.
Okay, so there has to be charge in the Yukawa term, right?
If you put sources in the Yukawa case, sources which produce this scalar field, then yes, there will be interaction, and there will be charges. Charge we associate to the matter. It describes the strength of interaction. Say, for instance, Klein-Gordon field with a say neutron inside the kernel, or like electron and positron interacts with electromagnetic field, and the strength of this interaction is measured by the coupling constant, which we call charge. And here what we consider a free electromagnetic field. There are no charges so far. There are no meta fields. So what I'm doing electromagnetic waves without sources. And the only thing which I do now, I'm trying to describe this formalism in a covariant way, where I don't make a distinction between time and space.
Yeah.
Okay. So we get this result. So we basically transfer the non-trivial commutation relations between P and A to the commutation relations between H and H dega. H with H commute and H dega with H dega commute. And so it is then clear that actually this commutation relation, which we have here, is due to oscillators, and in a way, this H's play the role of what is called Vierbinds. So this H mu on K can be expanded in the following way. I introduce what is called Vierbind because it has 4 legs, so H mu R, depending on K, and then I multiply it with oscillator of annihilation. Now I have 4 annihilation operators for all the photons, transverse, longitudinal, and time-like. So 4 oscillators AR, and analogously, I introduce H mu dega on K as sum R0, 3, H mu R on K, AR dega on K, like this. And what I would like to do, I would like to choose this Vierbind H mu R in such a way, I want it to be real. So I want it to be real. So this is not, conjugation does not act on it. I want it to be real, and I want to choose it in such a way that between these oscillators, AR on K and say S dega on K prime, the commutation relations will be canonical. Minus H bar, eta RS, delta K minus K prime. This is what I want. And so the question is how to choose such a Vierbind that these equations will be satisfied. Now, if you assume these commutation relations, then you can go to these relations here and actually substitute these expansions. And what you find is the following. So if you do this, you find, sorry, H mu on K, H mu on K, with H mu dega on K prime, equals to minus H bar delta K minus K prime, like this, multiplied by eta RS, HR mu on K, HS nu on K. This is what happens if you substitute, if you use this decomposition of H mu dega via oscillators. For oscillators, you postulate the standard covariant commutation relations, and then you come back and use this formula here. And so, therefore, this must be equal to minus H bar delta K minus K prime M mu nu. And by comparing, you find from here the condition that what should be there is the relation eta RS H mu R H nu S must be equal to M mu nu. So in other words, this Fairbairn must be such that being paired with the Minkowski metric, it should reproduce a matrix M mu nu. And in matrix indices, if you wish, or in matrix notation, this equation can be written as H eta H transpose is equal to matrix M. This is how it will look in the matrix form. This is a condition on H. Condition on H. Or equation on H. Equation to determine H. And it's when you look at this equation, this is already clear that solution of this equation is not unique. You can multiply H from the right by any matrix of Lorentz transformation, right? You see that if you multiply H by lambda, where lambda is a matrix of Lorentz transformation, then what happens is that you get here H lambda eta lambda transpose H, but lambda eta lambda transpose is eta by definition of what Lorentz transformation is. And so you will get H eta H transpose equals to M. And so this is a freedom. Freedom in the solution. Arbitrary Lorentz transformation can rotate H and nothing will be changed. In fact, this transformation by lambda, from the point of view of this oscillator algebra, if you think about multiplication from the right, you can attribute this multiplication from the right as an action on the oscillator, so the Lorentz transformation. But under the Lorentz transformation, you see that these relations will not change. So Lorentz transformation of these oscillators is canonical transformation. It does not change the algebra of oscillators. So this is a freedom we have in our solution. And one nice solution of this equation with the freedom taken into account is like this. So you can take this Fairbairn or Fairbairn as follows. Explicit solution I give to you. That is what I found. 3 lambda plus 1 divided by 4 lambda. Here, kj divided by k0, lambda minus 1 over lambda. Here, ki over k0, lambda minus 1 divided by 4 lambda, and here is also 4 lambda. And here, delta ij minus ki kj divided by k0 squared, lambda minus 1 over lambda. And as I said, from the right-hand side, so that's particular solution, but from the right-hand side, we can multiply it. We can multiply this matrix by any Lorentz transformation, matrix of Lorentz transformation. Lorentz. Lorentz transform. In fact, you see also that for lambda is equal to 1, this matrix turns to identity. And H simply becomes an arbitrary Lorentz transformation, which is a canonical transformation for oscillators. Again, you see the distinguished nice point, lambda is equal to 1. Now it is time to look at the Hamiltonian of our theory. So the Hamiltonian was quite complicated, but if you actually now what you need to do, you need to rewrite it in terms of oscillators, right? And all what you need is to take the Hamiltonian momentum. You can compute via expansion of a mu, and then you should substitute it into the expression for the Hamiltonian, and then you find the following quadratic form. So the Hamiltonian which arises in this covariant quantization approach, will take the following form. So integral over d3k, oops, sorry.
Professor,
Yeah.
here what you have written here, I, H, the matrix.
Say it again, please. I did not quite.
The matrix of H, lambda k, what you have written, I didn't. Okay.
The matrix H is now fixed up to an arbitrary Lorentz transformation. So this is the first matrix I'm writing here. This one is a particular solution of this equation. Particular solution. An arbitrary solution will be particular solution multiplied with an arbitrary Lorentz transformation.
Okay.
Sir, are these all the solutions? There are no other possibility.
No, there is no any other possibility. If you analyze this equation carefully, you will see that this is the only freedom you can have.
Okay.
That's the only freedom you can have. Matrix M, the right-hand side is fixed. It's a fixed matrix. The one which comes out from this explicit computation is this is matrix M. It is fixed. And then you see that the only possibility you have is multiply H from the right and use the invariance of the Minkowski metric under Lorentz transformations. I mean, of course, this matrix which you see here, it can be changed by changing lambda. So all the time you can say that part of the Lorentz transformation, so you can split Lorentz transformation since they form a group into product of two Lorentz transformations. You can take this lambda 1 and act on this matrix and bring it to some other form. But the general solution, if you fix a particular solution, then the general solution looks like a particular solution multiplied, a particular solution multiplied by an arbitrary Lorentz transformation. And I pick up this particular solution given by this expression because when lambda is equal to 1, it has a nice property to become just 1. Now you go to the Hamiltonian, you substitute an expansion in terms of oscillators, and you discover that this is a quadratic form in creation annihilation operators, which takes the following, which is given by the following expression. Beta mu nu, this is this matrices of Lorentz transformations, which remain to be undefined, and they enter into the Hamiltonian. Nu, say S, A dagger R on K, A dagger R on K, A S on K. This is how this Hamiltonian looks like, where B mu nu is a concrete matrix, which has the following form. So it's again a 4x4 matrix, which has the following structure. Again, I write it in the block form. So minus Ki divided by K0 lambda minus 1 over 2 lambda. Here minus Ki over K0 lambda minus 1 divided by 2 lambda. Delta Ij plus Ki Kj divided by 2 K0 squared lambda minus 1 over lambda. And this is how it looks like.
Sir, what do you mean by the lambda RS and lambda S nu here?
This,
are the H?
So this is the same as lambda here, but written just in the components. So this is matrix of Lorentz transformation. These are its components. So this is arbitrary. Yes, so they are arbitrary.
Okay.
They remain arbitrary, and you can understand them in two ways here. Either you think that they act on B, so they rotate matrix B by the transformation B goes to lambda transpose if you write it in terms of matrix indices, and this is lambda transpose B lambda. This is how it looks like. Yes, so this is pairing of this indices mu and nu from matrix point of view can be interpreted as the action of matrix B as lambda transpose B lambda. Or you can think that these lambdas rotate A dagger and A. And this rotation by Lorentz group is a canonical transformation. In any case, this lambda is a freedom, and if we would like to rewrite the Hamiltonian in terms of A dagger and A, which have a standard, no, not standard, but just Lorentz covariant commutation relation, like here, then this is the result. This is how the Hamiltonian will look like. And then idea comes that maybe picking up this Lorentz matrix lambda, you may bring this B to the most simple form. Because as I said, under this lambda, B transforms. And picking up lambda in a particular way, you may simplify this matrix B. And the first thing to try is to try rotations, just pure rotations. So lambda transpose B lambda. Lambda transpose B lambda. My pen does not want to write. Lambda transpose B lambda is a matrix of Lorentz transformation 1, 0, 0, R transpose with indices say I, M. So I take index here I and J. So this is matrix of Lorentz transformation, which in fact just a rotation. And rotation is a 3 by 3 matrix R. So this is R is a matrix of rotation. Matrix of rotation. And then there is a matrix B minus lambda plus 1 divided by 2 lambda minus ki k0 lambda minus 1 divided by 2 lambda minus ki k0 lambda minus 1 divided by 2 lambda, and here delta ij plus ki kj over 2 k0 squared lambda minus 1 over lambda, like this. And here 0, 1, 0, 0 R with indices n and j. And if you multiply these three matrices, then you will get the following expression here. It's just a straightforward multiplication. So you will get minus lambda plus 1 divided by 2 lambda here. Here there will be minus 1 over k0, lambda minus 1 over 2 lambda, vector k multiplied by matrix. So k here is from the left, so it's a row vector multiplied by a matrix with an index I. Here minus 1 over k0, lambda minus 1 over 2 lambda, krj. And finally, here is a 3 by 3 matrix, which has the following structure. KRI, KRJ. Like this, and the bracket is closed. And where R is just usual matrix corresponding to rotation, so R transpose R is equal to 1, is equal to identity matrix. No, and then it's clear that if you have a vector and or a row vector, and you act on this row vector by orthogonal matrix, you can always bring this vector to the form where it has only one non-zero component, right? only one non-zero component. It's like you rotate vector and put it on one of the coordinate axes by means of rotation, right? So you can always adjust, take a vector, rotate it, and put it on one of the coordinate axes. So in this case, only coordinate on this axis will be non-trivial, and coordinates along the other coordinate axis will be just 0. And so here we deal with the three-dimensional vector k, and it's clear then that you can always pick up the transformation R, rotation, such that you achieve that car R1 component is 0, car R second component is 0, kr second component is 0, and k r third component is simply coincide with the length of this vector k, and the length of this vector is k0.
Sir, can you repeat why it is 0?
No, this is because if you have any vector, three-dimensional vector, say this is a coordinate axis, you can always rotate it by means of orthogonal matrix and put it in one of the coordinate axes, along one of the coordinate axes, right? So that now it sits here by means of rotation. By means of rotation, you can always put it to sit on one of the coordinate axes. Then its coordinates with respect to the other vectors. So let's say this will be our vector k. Our vector k is here. And now by means of rotation, I put it along the third axis. So this is kr. Then its components 1 and 2 are equal to 0 with respect to the other axis. So this is x, y, and z directions. X, y, and z direction. So along the third direction, z direction, its component is equal to the length of this vector, because under rotations lengths are preserved. So this must be equal to the length of this vector. And the length of this vector is the same as k0. And the other components along the x and y directions are 0. Yeah, that's you can always do by means of orthogonal transformation.
Why you have taken this length here?
Sorry?
Why you have taken it as k0 length?
That's because k0 by definition is the length. That is something which we have postulated from the very, very beginning. That was a definition of k0.
Right.
Oh, yeah. So here, even earlier, I think somewhere, no, here. Trying to find where it was, just a second. Here. By definition, k0 squared is k squared. So k0 is a square root of k squared, so it's the length of this vector. And therefore, this matrix B takes the following form. So B in this frame, under fixing this lambda, this nice lambda, takes the following form: minus lambda plus 1 over 2 lambda, 0, 0, minus lambda minus 1 over 2 lambda, 0, 0, minus lambda minus 1 over 2 lambda. So symmetric form. Here is 1, 0, 0, 0, 0, again 1, 0, 0, and here 3 lambda minus 1 divided by 2 lambda. This is how matrix B looks like now. And I did further analysis trying to understand if this matrix B can be simplified further by considering now non-trivial Lorentz transformations, boosts, to try to understand if I can remove by boosts these off-diagonal components, and so to make matrix B completely diagonal. Unfortunately, I could not find Lorentz boosts. In fact, I think it's possible to show, and I think I did it at a certain point, to show that there are no Lorentz boosts which can remove from B these off-diagonal components. So matrix B cannot be completely diagonalized by means of these Lorentz transformations. But nevertheless, it does not matter, because then you just use this matrix B, substitute it into the Hamiltonian. So this is a new matrix B. So let's maybe call it B prime. B prime with indices I and J, and this is B prime, which we obtained. You see, anyway, it has a lot of zeros. It has a lot of zeros in it. And if you plug this B prime in our Hamiltonian, so this is essentially B prime with indices R and S, B prime with indices R and S, then explicitly, because of this nice form of B prime, we will get the following answer for the Hamiltonian. So Hamiltonian takes this form: integral dk omega on k a1 dega a1 plus a2 dega a2 plus a3 dega a3 dega a3 minus a0 dega a0 plus, this is all lambda independent terms, and then lambda dependent terms comes in the following form: a0 dega minus a3 dega a0 minus a3. So this is already normal ordered form of the Hamiltonian. And this is how it looks like. The Hamiltonian for generic lambda is non-diagonal because of interaction of a0 and a3 of this time-like and longitudinal photons. For lambda is equal to 1, this term disappears. This term disappears, and then you see this expression, which is nothing else as, if you wish, minus eta mu nu a mu dega a nu. Okay, so this is the Hamiltonian we get. And now we can consider really, I think, quantum theory by constructing the Fock space. So Fock space, what is this? So we assume that we have a normalized vacuum. And so vacuum, as usual, is normalized to 1. And then we start building up Fock space simply by applying to this vacuum all creation operators we have at our disposal. And so we say that this A1 and A2 are oscillators which generate for us transverse photons, transverse degrees of freedom. A3 we associate with longitudinal photons, and A0 we associate with time-like photons. So Hilbert space is very big. It contains, in addition to transverse photons of Maxwell, also time-like and longitudinal photons. And so the content of this theory is not the same as the content of the Maxwell theory. Moreover, we meet here another big problem, which was not there before. Let's consider one photon state. What would be a one photon state in this Hilbert space? This would be a superposition over all possible values of momentum, some function f on k, or any function f on k we can have, a0 dega k acting on the vacuum. So it's like a creation of a time-like photon from a vacuum. So time-like.
I think we also need to normalize it.
Sorry?
We also need to normalize it.
This is not necessary here. This is not necessary. You can pick up just the superposition of all the states. For the moment, I don't care about any normalization of the state. My point is different here. Time like photon. Let's compute as then.
What do we mean by time like photon? Because
photon which is created by A0 Dega.
But this photon doesn't travel at the speed of light.
Sorry? No. Time like it's because it contains index of time. That's why I call it time like. Not because it's it moves with the speed of light, so there is no point about it. The point I call it time like because this component here is 0 component corresponding to time.
Thank you.
And that's the only reason I call it time like. Like A3, I call longitudinal. And what I would like to do, I would like to look at the norm of this photon in a way. Maybe this is what you're asking about normalization. Yeah, so I want to have a look at what is 1 with 1. And we see that this is then dk prime, dk f star on k prime f on k sorry, f on k like this, and then there is 0 a 0 on k prime like this, a0 on k Dega vacuum. That would be the norm of this of this state. But then it's clear that what I have to do in order to compute it, I have to commute A0 and A0 Dega. And we can come back to the commutation relations for these photons and see how A0 and A0 Dega commute. And I recall you that they commute in the following way. A0 Dega on K prime is given by, on the right-hand side, as minus H bar eta 0, 0 multiplied by delta function K minus K prime. But eta 0, 0 is 1, right? So that's Minkowski metric, eta 0, 0 is 1. And therefore, when I will be exchanging this A0 and the 0 Dega by means of this commutation relation, in order to, for annihilation operator to act on a vacuum, on the right vacuum and annihilate it, what I will find because of this commutation relation is that I will get delta function K minus K prime, which allow me to integrate over K prime. And then what I find will be the following relation: minus H bar integral dk modulus of f on K squared modulus of f on K squared like this, which is obviously an expression which is less than 0. So because of these covariant commutation relations, which has now Minkowski metric on the right-hand side, its 0, 0 component produce such a contribution to the norm that the norm of this state appears to be actually scalar product of this time-like photon state with itself appears to be less than 0. This means that there are states in our Hilbert space which have a negative norm. This norm, in other words, is not positive definite, rather it is indefinite. So the Hilbert space or Fock space we are constructing, Fock space, has indefinite norm. Indefinite norm. And that's, of course, is unacceptable because we would like all the states to be physical and have obviously positive or non-negative norm at least. So having states with negative norm is, of course, physically unacceptable. This might look surprising, but we have to keep in mind that our Hilbert space is too large, as it accommodates, in addition to transverse photons, also unphysical time-like and longitudinal photons. And then we should not be surprised that it exhibits such unphysical features like an indefinite metric or an indefinite norm for some states. Well, now you may wonder that maybe all these unphysical features, too many degrees of freedom and definite metric, arise because we have not yet taken into account their gauge condition. Say d mu a mu is equal to 0. Since we are talking about covariant quantization, the natural gauge condition to impose is covariant gauge condition d mu a mu equal to 0, right? Because it's a covariant condition. But unfortunately, this condition cannot be imposed in the operatorial sense. It cannot be imposed on the operators. And that is clear from the following consideration. So if you take the commutation relation between P mu and A nu and differentiate the potential, then on the right-hand side, you get H bar divided by lambda d over d x mu delta function x minus y. So derivative sits now on delta function. So this derivative here goes to the derivative of the delta function, and obviously this is not equal to 0. So you may not put this d nu a nu to be some constant. For instance, you cannot make it 0, because if it's 0, then the commutator of P mu with 0 must be equal to 0, but it's not. But it's not because it contradicts to the canonical commutation relation between momentum and A nu and electromagnetic potential. So this means that I cannot impose this gauge condition at the operatorial level, at the level of operators. I cannot do this. Then one may try to impose this condition on states in this Hilbert space. So it's restrict, in other words, the Hilbert space to those states phi which satisfy, say, in the momentum space to the condition k mu a mu on k acting on state phi is equal to 0. Where this is a momentum space analog of this condition d mu a mu is equal to 0, right? It's a analog of this condition here. Going to being closer to the end of the lecture, for some reason my pen is not writing in a proper way. So d mu a mu is equal to 0 in the momentum space becomes k mu a mu on k is acting on phi is equal to 0. But it appears, however, that this restriction on states is too strong. Too strong. And in fact, it leaves no non-trivial states to exist at all. So analysis can be made which shows that this is, in fact, not possible. And then comes an idea due to two people, Gupta and Bleuler. Gupta and Bleuler. And the idea is to impose a weaker condition on states. Namely, if you take a part of a mu which contains annihilation operators, I call it negative frequency part of K, and impose it on states, then this is exactly what is needed in order to eliminate the unphysical degrees of freedom and make and also remove from the Hilbert space the states with negative norm. And so the quantization, covariant quantization approach, where you impose such a restriction on the Hilbert space on the Fock space created by all possible kind of photons, transverse, longitudinal, time-like, is called Gupta-Bleuler quantization. So when you hear the words Gupta-Bleuler quantization, that's exactly the covariant quantization with imposition of this constraint on the states in the Fock space or in the Hilbert space, in other words, constructed in the covariant quantization approach. Now, if you compute this expression, if you take K mu A mu minus on K, then you can see that it's actually proportional. If you take our A mu and multiply it with K mu, you will see that it's proportional to lambda plus 1 divided by 2 lambda, K0, A0 minus A3. So this is how it looks like, which suggests to introduce two operators. Operator L, which contains this combination A0, A3. So annihilation, difference between the annihilation operators of time-like and longitudinal photons, and introduce L dega, which is A0 dega minus A3 dega. So introduce two such operators. And since this is a condition you impose on phi, this means that the condition you impose on phi is actually the condition L depending on K acting on phi is equal to 0. This is the condition you impose. So combination, this particular linear combination of A0 and A3 acting on phi is equal to 0. So these conditions are compatible because for different chi's you can check, that comes from the original commutation relations, you can check that this means that L on K and L on K prime, they do commute, and therefore imposition of these conditions on phi is possible. This is a consistency condition, in fact, of these relations. Moreover, you find the following, that if you commute L on K with L dega on K, then this is the same as A0 minus A3 with A0 dega minus A3 dega, like this. Now, non-trivial commutators arise between A0, A0 dega, and we have seen that this is minus 1, plus commutator between A3 and A3 dega, but this will be plus 1 because a metric has an opposite sign, which on the right-hand side of this commutation relation. And so you will get here plus 1, and so the result is 0. So L and L dega, they do commute between themselves. And so generic solution of this condition here, of this condition, can be written in the following way. So phi looks as follows. 1 plus sum from n equals 1 to infinity, integral, function f depending on k1 and so on, kn, product I is equal to 1 to n dki divided by square root of 2 omega on k. That's normalization. not so essential here. L plus, depending on Ki. And this all act on phi, on a state which is created from the vacuum by the transverse photons. So this part is a state created which contains in it only transverse photons generated by A1 dega, A2 dega. Then there is this tail of oscillators created by L plus, and if you act on this state by L plus, sorry, L dega by plus, I mean dega. If you act on this state with L, since L commutes with L dega, as we just have seen here, then L will pass through L dega, act on phi transverse, but L commutes, of course, with A1 dega, A2 dega, it comes to the vacuum and annihilates it. So these states represent a general solution of this condition here. So this is a general solution. In particular, in the Hamiltonian also, the term which depends on lambda, you saw this term here, it's written as L dega multiplied by L. And so when you act by the Hamiltonian on such a state phi, since it is annihilated by lambda, then this term on such states simply decouples. And your Hamiltonian becomes to have the same form as for lambda is equal to 1. So on such states, the Hamiltonian simply becomes a quadratic form, dk omega dk omega on k is A1 dega A1 it's not writing. A3 dega A3 minus A0 dega A0. This is how the Hamiltonian simplifies on the states of this type. Moreover, there is a further simplification because these two terms here, you see, they contain longitudinal and time-like photons, but this term can be written in the following form. If you think a little bit about it, it can be written as A3 dega minus A0 dega multiplied with A3 minus plus A0 dega A3 minus A0. Minus A0, like this. And yeah, you see, so this term here cancel this term here, and then you return back to this expression here. But this is written as L dega A3 plus A0 dega L. And so now you see that on average, if you plug this Hamiltonian between two states which satisfy the Gupta-Bleuler condition, then actually because of L dega acting on the left phi annihilated, and L acting on the right phi annihilated, then this will be the same as sandwiching the Hamiltonian between two orthogonal states which are created only by the transverse oscillators. And from H, original H, the contribution will come only from this spot, which I denote by H transverse. So H transverse, if you wish, is the same thing, but with transverse oscillators only, like this. And in other words, when we are interested in the averages over the states, such states in the Hilbert space, then results, these averages, do not receive contribution from time-like and longitudinal photons. Okay, I think this is almost all what I wanted to tell you. The only thing is that we still have to consider the issue of propagators in this covariant gauge approach, but this I will do in the next lecture. This is very simple to finish our discussion. The only thing, maybe the last one I will tell you, is that the states in this new subspace of the Hilbert space, there are states which have zero norm. And these are states which do not, which states which have zero norm due to this contribution from L plus, because if you compute now the, say, norm of such a particular state, then it will look like K1 L plus on K prime, K1 K1 prime, Kn prime, L on K1, L on Kn, vacuum. Well, other way around, maybe I have to put pluses on the other side, yes, as creation operators. And then you multiply it by two functions depending on K and K prime and integrate. So you compute a norm of such a state on K and phi on K prime. So norm of such a state, and then you integrate over dk and dk prime. Then because of L and L dagger commute, you can put all L dagger to the left and all else to the right. And when they will be acting on the vacuum, you'll produce zero. That means that in your Hilbert space, in spite of the fact that you impose the Gupta-Bleuler condition, there are states which have zero norm. And if you want to obtain just the physical Hilbert space without the states with zero norm, the only thing you can do it, in fact, is to consider a factor space of this Hilbert space without negative states, which is obtained by imposition of the Gupta-Bleuler case. You can consider a fractal space of these states over space over states with zero norm. How to denote them? States. Okay, let's write it just states which have zero norm. So in other words, taking a fractal space, and this gives you a physical Hilbert space. In fact, states with zero norm, they correspond to states which are responsible for gauge transformations. That is possible to show. States with zero norm, they are responsible exactly for the gauge transformations for electromagnetic potential. And taking a fractal means that I do not distinguish in my physical Hilbert space two states which differ from each other by a state of a zero norm. That's what means taking a factor. So I agree that two states which are differ from each other by a state with zero norm are considered to be equivalent. So in other words, we define the physical Hilbert space as a set of equivalent classes, the Hilbert space of Gupta-Bleuler over the states of the zero norm. Okay, that is what is concerned covariant quantization, and I think I will finish with this. And if you have quick questions, I can answer. Otherwise, there will be another lecture in 10 minutes, and so we have to hurry a little bit. So my plan for the next lecture is to explain to you what happens with propagators in this covariant gauge approach. Then we finished with quantization of electromagnetic field, and we go to another big subject, namely to scattering theory, quantum scattering theory. We will discuss the construction of the scattering matrix in quantum field theory.
Yes, sir.
Okay, thank you.
This is the last part, that is L3 dagger A3 plus A0 dagger L is related to some UV divergence here.
No, this is not related to that.
Because we are considering here normal ordering.
Yeah, and normal ordering, yes, normal ordering we fix it in order to make all the operators well defined when they act on the vacuum. But even with the normal ordered operators, there will be divergences in this theory. So normal ordering does not prevent all possible divergences in this theory. They make our operators well defined, well behaved when they act, say, on the vacuum state. They remove sort of obvious divergences which are related to such things as, for instance, self-energy and so on. But they potentially do not remove all the divergences we have in quantum field theory. We will see it very shortly that they do arise. Okay, if you don't have any further questions, then we will see each other and hear each other next Friday. Okay?
Yeah. Thank you, sir.
So I wish you a pleasant day, and bye-bye till Friday.